Okay, welcome back. We have a little bit of a shorter day today. The topic is differential and integral operators. In fact, it's a pretty tiny subset of maybe the full class of differential and integral operators. But I'll go through what the book has. And the book just wants to reference right away, thinking about, matrices are not required to be square, and we can definitely map an m-dimensional space to an n-dimensional space. And our linear operators can do something very similar, right? We can start in an infinite dimensional space and end up in an infinite dimensional space, but those spaces don't necessarily have to be the same. You can interpret like this L2 of 0 to L as one infinite dimensional space, and you can interpret like the space of Taylor series as perhaps another infinite dimensional space, and those two they're not the same space. And you can map from one to the other using still an operator, but it doesn't necessarily need to input and output the same sort of space. So thinking about we're jumping into differential operators. These are just operators that contain at least one derivative inside of them. It's important to note that these have a null space. There is a null space. Say there exists a quote unquote null space. It shouldn't even be quote unquote, but I'll use a quote here. There's a null space for ddx, the same way there would be a null space for a matrix. These are the vectors which get sent to 0. And in fact, the null space for ddx is the constants. It is the constant functions. And so it's important to notice. So in some sense, this is like the derivative is eliminating a single dimension of our space because it reduces the constants, which are a non-zero direction to go in. It reduces them to 0 no matter what they were. And so in some sense, the derivative is like mapping infinity to infinity minus 1 dimensions. Now I know that's like a weird way to think about it, but that's what I kind of mean to say when you think about the derivative. And we can actually extend the differential operators. So there's your maybe generic. This is your linear operator equation. This is a generic linear operator equation, and think in this equation along the lines of m vector equals another vector, and then would be solved by v is m inverse on b. We maybe have a question about inversion. What would it mean to compute L inverse G? And this is kind of an important question because in some sense L inverse G, along with this interpretation of V as M inverse B, is the solution to whatever this equation would be, this more operator valued equation. Okay, so jumping back to maybe the Poisson equation, this is where we let L be a differential operator, negative d squared dx squared. If I take two derivatives in f, that equals g. This is precisely the Poisson equation. So the Poisson equation we were used to back in our PDE section, and I know in its current form it's just an ODE, this Poisson equation can be rephrased as just an operator equation with a linear operator L, and to solve that equation would mean inverting the L. A different maybe differential equation that you could represent with linear operators would be a differential equation with just a capital D representing the derivative, and then it's just d dx of f of x equals g of x. And then this jumping at the bottom, this is perhaps maybe your most, not the most general, but this is a general second order linear ODE can be represented as a linear operator equation in the sense of, LF all of a sudden is now written as P of x times two derivatives on f, Q of x times one derivative on f, R of x times zero derivative on f, and then the equation LF equals G is really a second order linear ODE, right? It would look like that equal to G of x, and that's your generic second order linear ODE. We can also think about differential operators like the curl or the divergence. You encountered these back in our kind of our Calc 3 subsection. The curl as an operator, right? It mapped, in some sense, it was a vector field. So you had three functions, v1, v2, v3. Each of those functions were independently infinite dimensional. So this was really like a 3 times infinite dimensional space. And it mapped it to, the curl, which I guess was something like, it was like partial v3 partial x minus partial v2 partial partial v3, partial y, partial v2, partial z, and then you had some other terms here, and that was just the curl. But each of these entries here, that was a linear operator on an infinite dimensional space. That's a linear operator on infinite dimensional space, and then you combine those very particularly, and you recover like a linear operator on 3 rounds of an infinite dimensional space, and that's what the curl operator is. Versus the divergence kind of took in, right, this mapped a 3 times, this was the same sort of input, except all of a sudden it mapped it only to a single function, right? This was now partial v1 partial x plus partial v2 partial y plus partial v3 partial z. This one combined 3 linear operators in infinite dimensions. It took in 3 times infinite dimensional space, but it only output a single infinite dimensional space, because this is a single function that you received as an output with the divergence. And so this is kind of referencing that we can map each of these vector spaces are infinite dimensional, that the derivatives act on. But in some sense, we're replacing R here with a function space, something like L2, 0 to L, and that L2, 0 to L can be in M or N dimensions, right? So you can take that and embed it into a dimensional space and send ourselves to L2, 0 to L of maybe, M copies of that space or something like that. And these curl and divergence operators do something like that for us. And we can also represent differential equations just as operator equations. So that's what we want to think about when it comes to differential operators. Integral operators kind of do the reverse. A lot of them, I should call this maybe definite integral operators, actually take us from an L2 space or some sort of function space, an infinite dimensional space. And a lot of times they'll just send us into R. They'll send us to some positive number, because think about it. If I start with f of x, and maybe I act on it with L, and the way that I define L is maybe an integral from 0 to 1/2 or something, f of x, and the output of this operator, this is a perfectly linear operator, but its output here is real valued. I've all of a sudden eliminated all of my dimensions, and I just recover a real valued output. And so now I've reduced from infinitely many dimensions down to 1. And that's really something that's special about these operators, that we can send ourselves from infinite dimensional spaces to 1, or vice versa. We're not going to get into the vice versa. It's not that important what those would look like, but let's give some examples of maybe integral operators now. So one of them is just the norm, right? We could take the norm. It's not, okay, so this is not by itself, it's not a linear operator. The norm is nonlinear because we are taking a square root and actually we're squaring something. But it is an integral operator because it maps an infinite dimensional space into a finite dimensional space. And so you can think about that as one of your integral operators. You can think about the probability operator, right? This was computing the probability that a function or that the particle was found in the interval a to b, and you would integrate from a to b. You'll recall this would be like if psi is our wave function and x is a position, then psi describes the probability distribution of a particle, and if I restrict my range from a to b, then I get the probability within that region. So that's all I have for you today. Like I said, it's a little bit shorter. I'm going to share a second video with this one to kind of reinforce the notion of operators in infinite dimensions. But anyway, I'll see you in class. Bye.